with sedimentary rocks, erosion is the transportation of sediments that were broken up rocks from the process of weathering. There are a number of things in nature that can transport or erode material. For instance, gravity does a great job of just pulling material downhill. Gravity is the cause of landslides and mudslides and rock falls. Gravity can cause houses to get pulled downhill. We also have rivers. Here we can see that the river is eating away the weathered rock material or the soil that these tree roots are growing in. Rivers also move muddy water. The reason that water is muddy is because there's a lot of sediment in it. As that sediment gets moved, that is erosion, the movement of sediment. There's also wind. Wind does a good job of blowing material away. Here we can see that this rock, as it gets weathered and broken apart from the abrasion of the other sand, gets pushed and moved away. Glaciers do a great job. This glacier, as we look at all over this glacier, you'll notice that it looks dirty, and that's because glaciers are full of sediment, everything from fine powder to massively large boulders. So glaciers do a great job of eroding or transporting material, as well as waves. When waves hit the shoreline, they usually don't hit directly at a perpendicular. They hit at an angle, and that moves the material along the shoreline. Our focus today is going to be on rivers, specifically how a river's velocity affects stream erosion. One of the things I want you to understand is that the fastest part of the river is going to be in the middle of the river, just below the surface. There's going to be friction with the banks of the river and on the side, and there'll be a little bit of friction also with the atmosphere, the air up there. So the fastest velocity of a river is going to be a little bit below the surface in the middle of the stream. Looking at this picture right here, can you tell whether river A or B would be flowing the fastest? Yeah, you can tell just by the picture that A is moving the fastest. A or B? In this case, stream A is moving faster than B. And again, we can see here that B is moving faster than A. In all three instances, the reason the river is moving faster is because it's going down a steeper hill or an increased gradient. The faster water is going to move when there's a steeper hill. That's not a surprise at all. If we increase the gradient, and gradient means steepness, we'll increase the velocity of the water. So the fastest water is always in the middle, just a little below the surface, and if we increase the gradient, that will increase the velocity of the river. Another thing that affects the velocity of the water is how much water there is. So we could see here in this nice stream that there's water flowing, but there's not a lot. Certainly not very deep. We could easily walk across that and just get our ankles wet. But if the water, if it rains, we can now have more water, which would increase the velocity. You can see some of these large boulders that are here. They're not going to get moved by that slow moving water. If we increase precipitation, the amount of rain or snow melt, now we have more water in the river, and it's going to be moving faster, and it's going to be able to erode or transport some larger pieces. You would imagine that first stream, that very small pebbles or sand might get moved along. Here, we can imagine some pebbles and sand easily being pushed by this water because it's moving faster. The reason it's moving faster is there's more water. Increasing precipitation or rain, we now have much faster moving water because there's more of it. We call the amount of water flowing through a river the discharge. Here we can see a river that changes its discharge over time. Usually just a small little stream next to this parking lot. Over time, this river increases its discharge or the amount of water, therefore increasing its velocity to the point where it overflows and actually moved some of these cars out of the way. Increasing rainfall leads to an increase in the amount of water, or the discharge, which increases the velocity. The faster that water is moving, now the larger pieces of sediment and cars it's going to be able to carry. Stream discharge can be measured. We can go out and actually set up equipment to measure the amount of water that's flowing through a stream. If we know how deep the water is and we know the speed, we can calculate the volume of water that flows through down a river at a certain time. Sometimes we can't, and we'll just have to estimate. Here we could see two pictures of the same river. Notice in the top picture, there's very little water, the water's moving slowly, and the bottom, more water moving a lot faster. In page 6 of the reference tables, there's a chart that shows us this relationship, that as stream velocity increases, the size of the particles that can be eroded or transported also increases. This chart is a little different than we're used to seeing. On the vertical axis, we can see that there's 0.1. After that is 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1. But the next step after 1 is going to be is not 1.1, instead is going to be 2. So once we reach one of those solid lines, we now start counting by a different amount. Instead of counting by tenths, now we're counting by 1. And the same thing is true not only here on this chart. So if we look at this, there's 1, there's 2, 3, 4, 5, 6, 7, 8, 9, 10. That next one is 20. The vertical axis is this way, as well as the horizontal axis, which shows us how fast the water is moving. The vertical axis was showing us the particle diameter, or the size of the sediment that can be pushed. We have the horizontal axis, which is showing the velocity in centimeters per second. And again, we have 2, 3 centimeters per second, 4 centimeters per second, 5, 6 centimeters per second, 7, 8, 9, and 10. But over on this side, now we count up by tens now. 20, 30, 40, 50, and so on. So please be cautious about the both vertical and horizontal axis and how it counts. It's a little bit different than we used to. Included on this chart is something that we saw before when we talked about sedimentary rocks. You could see that there's different sizes, clay sizes, silt, sand sizes. And if you compare these sizes to your page 7 of the reference tables on the sedimentary rock ID chart, you'll see the same numbers, such as sand ranges from 0.006 centimeters to 0.2 centimeters. So that information is given to you on this chart as well. Anything below this dark line that goes through the middle of the chart is erosion, meaning the material can be moved or transported. Remember, transportation means erosion. Erosion means to bring the material from one place to another. So anything on that side is erosion. Let's take a look at some questions, some practice questions to learn how to use this chart. The largest sediment particles that can be transported by a stream traveling at a velocity of 200 centimeters per second are, what's the largest sediment? Well, if it's 200 centimeters per second, I'm going to draw a line from 200 centimeters per second up to that line. Everything below that line can be transported, can have erosion. So clay can be transported, silt can be transported, sand can be transported, pebbles can be transported. And cobbles up until a medium-sized cobble can also be transported. So the largest sediment that can be transported is cobbles, or choice B. Second question, the largest particles that a stream deposits as it enters a pond are 8 centimeters in diameter. The minimum velocity of the stream is approximately. So notice we're given the size of the particles now and where to find the velocity. So if it's 8 centimeters in diameter, that's going to be right there. Remember, these numbers count by ones: 1, 2, 3, 4, 5, 6, 7, 8, between 1 and 10. We go over to the line. What size pieces do we see? Well, we see the small cobbles, which would hit a little bit to the left of that line. That line is the 200 line. So maybe we're guessing around 180 or so. They also, you'll notice that the tick marks on the bottom and the tick marks on the side, tick marks on the bottom and the tick marks on the top match up. So it's easy for you to draw a line when we're trying to find exactly where something is hitting. 3, a stream flowing at a velocity of 75 centimeters per second can transport. If it's going 75 centimeters per second, what material can it transport or erode? Transport and erode, synonymous. So I find 75 centimeters per second, and it can erode anything up to that line. So it can erode clay, silt, sand, and most pebbles. Our choice would be C: pebbles, sand, silt, and clay. 4, what is the minimum water velocity needed in a stream to maintain the transportation of the smallest boulder? So again, it's asking us to find the speed. The size is not given in centimeters, but is the smallest boulder. So let's find where the smallest boulder is, right there. Smallest boulder, how fast does the water need to be moving in order to transport that? Well, we draw the line down from smallest boulder on down, and we see that it's hitting 200 centimeters per second. So now we need a velocity that would transport cobbles, but not transport boulders. Well, there's cobbles, there's boulders. So there's not much that fits into that area right there, but maybe something around 180, 190 centimeters per second. It's pretty close. All right, there's your notes for page 35 in your green notebook.